Hello, everyone, and welcome to Professor Fahimi's ENA exam review. So, in this review, I'm just going to go over theory, but I'm also going to do a few example problems. But then on Monday, 2 days before the exam, it's on Wednesday, October the 2nd, I'm going to hold a live session on Teams doing the exam from last year. So, I'm on the syllabus, and it looks like exam 1 is just a bunch of resistor networks. So, alright, yeah, cool. Let's go ahead and get started. Let's see, all the way up until here. Oh, and there's energy storage elements. Okay, that's good. Alright. Resistor networks. Alright. So the first topic is Introduction to Fundamentals. That's probably just Ohm's law, so that's review. Then we got Kirchhoff's laws, that's also review, and then resistor circuits. Okay, so I'll go ahead and start from there. That's also review, but it's a little different ENA. So resistor networks. So resistor networks are basically independent or dependent sources, like voltage sources and current sources and such, like this. I'm just going to draw a random circuit. Maybe get a dependent source in there too. So it's basically any circuit that has only resistors. Say if I put this in a black box and then only care about the two terminals coming out, well, this could just be written as a network, or it's just a resistor network, which basically just means there's only voltage sources, current sources, dependent or independent, doesn't matter, and resistors. So that means no inductors and capacitors. So let's go ahead and see the techniques of how to solve them. So the two main techniques are the nodal analysis and mesh analysis. But before we get to those, there's two main resistor networks that are important in ENA. So the first one, let's go ahead and write, we're doing resistor networks. Home things, networks, not N. Resistor networks. So the two main resistor networks is, the first one would be the voltage divider. So a basic voltage divider would just look something like this. You have an independent voltage source, and there has to be at least two resistors. So I'll call this VS, R1 here, and R2 here. So the voltage divider basically means the circuit takes the voltage source and divides the voltage drop between these two resistors. So let's see how that happens. So if you write a loop equation, then that's the KVL. We get that VS is equal to the voltage across R1 plus the voltage across R2. And then we have to write these voltages across resistors in terms of the current, because you know the current in this circuit is the same because it's a series connected circuit. So this equation becomes VS equals, well, we know Ohm's law, V is equal to I times R. So I stays the same because it's series, I times R1 plus I times R2. And notice we can factor out one of those I's, or both of them, to one I, so we get VS equal to I times R1 plus R2. And notice that when you solve for the current, that would just be I is equal to, well, we'll just divide by that R1 plus R2, so it's VS divided by R1 plus R2. And so this is good. Now, we can do with this I, is you can multiply it by R, because V is equal to IR. Remember from Ohm's law, I'll just write up here. V is equal to IR. Remember, that's Ohm's law. So this I, if I multiply it by, for example, R1, then that would be the voltage across R1. So let's do that. We have to multiply by R1 on both sides, like this. So remember, this would simply, on the left-hand side, R1 times I, well, that's just the voltage across R1 from Ohm's law. So now this becomes the voltage across R1 is equal to VS times R1 over R1 plus R2. And if you notice, the voltage across R2, similarly, it's going to be Vs equals to, now in the numerator, we have that resistance, the one we want to solve for, the voltage across it, is now on the top. R1 plus R2 on the bottom. So notice the structure of the voltage divider, it's always, so like for example, if you want to find the voltage across R1, this voltage here, this is VR1. Well, it's simply going to be that resistor you're looking at, R1, divided by the sum of the two resistors, multiplied by the input voltage. And that's how you find the voltage across each of these resistors. So notice if you had 3 resistors, you would have a sum of 3 resistors on the bottom, and then the resistance you're looking at. Oh, sorry, there's a Vs here. Sorry. So yeah, those are the equations for the voltage divider. One of the important resistor networks. So the second one would be the current divider. So the current divider is the same concept. So 2, the current divider. So usually this one is written with a current source, IS, and then 2 parallel resistors. So notice the voltage divider was a series connected circuit. Now this one's parallel with the current source. So it's like a dual relationship. They're called duals. You have voltage and current is a dual. And then for resistance, let's draw that. Sorry. For resistance, the dual, well, you can imagine it's going to be the conductance G, which is 1 over R, just the reciprocal of R. So for this current divider, we were going to use the KCL instead of the KVL. That's another dual. The Kirchhoff's voltage law, or the loop law, and then there's the KCL, the dual relationship. So this current flowing to this node's going to be the unknown voltage V1, and then the ground reference, I'll choose it to be here. So this I right here, I'm sorry, it looks bad. This current flowing into the node from this branch is going to be, well, that's just IS. And then the current through these resistors to ground would be the unknown currents. So I'll call it I1 for this one and I2 for this one. So from KCL, remember, KCL states that the current going into a node equals the current going out. So the current going into this node is going to be IS equals, because every other current is going out of the node, is equal to I1 plus I2. And so just like the voltage divider, you have to write this I1 and I2 in terms of the unknown voltage V1. So it's going to be IS equals, well, I from Ohm's law is V divided by R, or G times V, where G is 1 over R, remember. So IS is equal to, well, I is V1 divided by R1 plus I2, well, it's just going to be V1 divided by R2. So then you can factor out the V1. IS is equal to V1, all multiplied by this, 1 over R1 plus 1 over R2. So now you solve for V1, we get V1 equals IS divided by 1 over R1 plus 1 over R2. So now, remember, I equals V divided by R. If you take this V1 and divide it by either R1 or R2, then you get the current in that branch. So let's test it out and see it. Let's take this V1, and first let's divide it by, let's just do R1. V1 over R1 equals, so you have to divide R1 on both sides. So then we get, remember, this is Ohm's law, this V1 divided by R1. So that's simply I1, that's what we wanted to solve for, equals, well, dividing by something is just multiplying by 1 over. So we end up getting this. IS divided by 1 over R1 plus 1 over R2 multiplied by the reciprocal of this, which is 1 over R1. So simply, you notice it's the same structure as a voltage divider. We can see that if we write it in terms of its conductance. I1 is equal to, well, IS times 1 over R1 is G1. Then we got G1 plus G2 on the bottom. And that's the current divider, where G is simply just 1 over R. So it's the same structure of equations as a voltage divider, except it's easier to write in terms of the conductance, or just 1 over R. So those are the two basic resistor networks before heading to the techniques to solving them, which are the nodal analysis and the mesh analysis. So what are those? I'll keep that up there. Still a part of resistor networks. So it looks like the first one on the syllabus is the nodal analysis. So what does that mean? Well, to start, I'll draw a simple circuit like this. Just a simple resistor network. Just making this up. Just draw a bunch of resistors here like that. Just say this is R1, R2. Let's call this R3. Let's make this a current source. Let's call this V1 and I1. So this is a simple resistor network that we're going to solve using the nodal analysis technique. So the first thing you do is you want to pick your reference point, or they also call it the ground, which is basically, because voltage is a measurement between 2 points, the ground is your reference from the high side of the voltage to ground. So those are your 2 points to measure voltage. So that's the first step. The second step is you write the KCL in the circuit. So you have to observe that in nodal analysis, in nodal analysis, the n unknown, how do you spell it? Unknown nodes, sorry, it's bad. Unknown nodes equals n number of equations. Number of equations. So in nodal analysis, you want to count how many nodes you have. Actually, yeah, you want to do that before writing your branch currents. So notice in this circuit, there's an unknown voltage here. I'll call it VA in this node, because we don't know what the voltage is here, respect to the ground we chose. So that's the whole point in nodal analysis. You want to find the unknown node voltages. Oh, sorry. So let's go ahead and see how to do that. So the basis of nodal analysis would be the Kirchhoff's current law, because you'd have to draw currents like this. Say this is I1 through that resistor, R1, and this is I2, and then we'll call this one through R3, I3. I3. So then we write the KCL, which is going to be current going in equals current going out. Well, that's just I1 is going into the node, and so is I3. So we add those together. Equals the current going out. Well, that's I2. Now we write these currents, these branch currents, in terms of the voltages. So this current, I'll start with I1. This current, well, remember, I equals V over R. But how does that apply to nodal analysis? Well, the more general version of this would Ohm's law, I equals, well, it's going to be the high side of the V minus the low side of the V, or the high potential minus the low potential. Because remember, voltage is the potential between 2 points, say for a resistor. I'll just call this part the high side voltage and this part the low side voltage. Because remember, the voltage across this resistor is going to be VR is equal to V plus minus V minus. You take the higher potential and subtract it from the lower potential. It's almost like an elevation. That's pretty much what voltage is. So actually, I'll keep that there for now. So given that, I1, well, we know at this point in the circuit, that's going to be the voltage V1. So we'll start that. But then we have to subtract this voltage here, this unknown voltage, V1 minus VA. And then Ohm's law says we have to divide by R. So yeah, this would actually be divided by R. Oh wait, no, that's current. The current is V over R. So this current I1 is, remember, this voltage at this point, which is V1, because this voltage source is pushing the voltage here to be V1. Then you have to subtract the lower potential, VA, divide by R1. And another easy way to know like which way you go, like V1 minus VA, well, notice this current I drew it going in this direction from V1 to VA. Because remember, current conventionally flows from high to low potential. So that's just my convention. I'm following the arrow. It goes from V1 to VA. So that's the way I've subtracted. So now we have to add I3. Well, notice I3 is simply this branch, and the current is already defined. So the current I3 is simply I1. And this could be equal to I2. So I2, remember the same thing. We take the high voltage and follow the arrow. So it's going to go from VA to ground. Remember, with ground 0 volts, this is 0 volts. VA minus 0 divided by R2. VA minus 0 over R2. And so once you have this equation, so remember, these two in a problem, this V1 and I1, those are going to be given. So then you just solve for VA, which, like nodal analysis is, we have one unknown node and one equation. So that's how nodal analysis works. So I'll go ahead and do an example. Guess I'll just find one on the internet. Let's see, just example. Let's see if there's any interesting ones. Let's see. That one's alright. Let's see. I want to find one with a mix of voltage sources and current sources. Let's see. Here, I'll find this. See if that gives a good one. Let's see. I'm trying to find also one that's not like weird. Like these voltage sources are like pushing down. Those are a little bit different. No. Okay, this one looks cool. So let's go ahead and solve this one using nodal analysis. So it says, let's see what the website says. Use nodal analysis to obtain V0. All right, let's copy that. Okay, so this is the problem. We have to use nodal analysis to find V0 in the circuit. And V0 is this node here. All right, so in this circuit, we observe there's only one unknown node, which is V0. So we have to, and ground's already defined, it's right here. So then we have to write the KCL. Oh, nice, they already drew the I1, I2, and I3 for us. So that's cool. So we have to write the KCL. So remember, current going in equals current going out of the node. It looks like all the currents are going out, like this. They're going out. So that means current going in is 0 equals the current going out, well, I1 plus I2 plus I3. And then we write the nodal analysis equation. So I1 is going to be V0 minus this point in the circuit, well, that's 12. Minus 12 over R, which is 4. Plus I2, well, that's going to be V0 minus 0 over 6 plus I3, or we're going this way, we're being it's going to be, so at this point, it's V0, the unknown voltage, and then we're going this way, then we hit 10, and then we hit 0, divided by 2. So it's going to be V0 minus, we have to subtract that 10, minus 0, all divided by 2. And remember, this whole thing is equal to 0. So now we wrote the null analysis equation. It's now an algebra problem. So notice there's only one equation and one unknown. So it's no longer a circuit problem. It's now just algebra. So I'm not going to get really too much into those. You can use whatever tool you want, Matrix or MATLAB. Well, this one you just solve for explicitly. It's just a bunch of numbers you have to simplify and then solve for V0. So I'm actually going to go ahead and do another example. Maybe a little more difficult one. Let's see if there's any hard ones. Hard nodal null analysis problems. Let's see. Wow, that one looks lengthy. Let's see. This one looks more interesting. Let's go ahead and do this one. Write the equations. Alright, so now we have this one. And we're supposed to find, what are we supposed to find? We want to find V0 using nodal analysis. Alright. Find V0 using nodal analysis. Alright, so V0 is this node right here. Okay, so first thing, we have to define our ground. I'll choose it to be here. Then now we write the currents. So let's see. I'll call this I1. This will be I2. This will be I3. And this will be I4. Alright, so now we write the KCL. So now there's two nodes. So first I'll do the KCL. So I have to write two KCLs. I'll do the KCL first at V1. So that's going to be, well, at V1, we have, remember, current going in equals current going out. It looks like there's no currents going into V1, and there's only currents flowing out. So that's going to be 0 currents flowing in equals, well, I1 is flowing out. So is I2, this one right here, and so as 5 amps. So it's I1 plus I2 plus 5 equals 0. Okay, now let's write the nodal analysis equations. So I1 is going to be V1. The number got cut off. Oh, that's 40. Okay, hold on. Let me take that in. Another screenshot. There you go. Actually, let's do this. 40 volts. Okay, so it's going to be V1 minus 40 minus 0. So I'm just following the arrow. So V1 minus 40, then minus 0, divided by 1. So that's I1. Plus I2 is going this way. Well, that's V1 minus V0 over 2. Plus 5 is equal to 0. So that's equation number 1, the first node equation. So there's two unknown nodes in the circuit. So I'll have to have another equation, which will be node V0. So I'll have to write the KCL at, KCL at V0. So let's see with the currents flowing in, the currents flowing out of V0. So currents flowing in, I see the first one, it could be 5, that's flowing into V0, plus I2 is also flowing in. And it looks like those are the only currents flowing in to V2. The rest are flowing out. So current flowing in equals current flowing out. Well, the first one's going to be I3 plus the second one, that's I4. So then write the nodal analysis equations. 5 plus, well, I2, remember, is V1 minus V0 over 2. Plus, equals I3. Let's see what that one is. I3 is going to be V0 minus, well, that's ground right here, so that's 0 divided by 4 plus I4, well, that's V0 minus, and so this voltage source is upside down, so by convention you could write it this point, well, that would be negative 20. That would push this point to 0 because we want to keep this node consistent if it's ground. It has to be a potential 0. That would mean this source, by the convention of ground, this is 20 volts at this node. So it's going to be V0 minus negative 20 over 8. And so that's equation number 2. So remember, the basis of nodal analysis is the KCL. So you have to first pick your reference voltage, which is usually at the bottom of the circuit, but you can really pick it wherever you want. It's just easier away from all these like unknown nodes. So you will usually pick it here at the bottom. Second, you draw your currents as such. By convention, determines whether how you subtract your potentials. So you just follow the arrow. It goes from high to low. And then that's this step. Then you write your equations, your branch currents in terms of the voltages using Ohm's law. And then after that, it becomes an algebra problem, no longer a circuit problem. And that's honestly one of the most time-consuming parts of these questions, which you can put it to a matrix to make it easier, and also MATLAB is a good tool. But I'm pretty sure during the exam you can use, it's open note for Dr. Fahimi, so you can just open up MATLAB and solve the algebraic equation. So that's it for nodal analysis. So next technique to solving resistor networks would be the mesh analysis. So it's number 2. Mesh analysis. So mesh analysis is the other technique to solve resistor networks. And so if you think about it logically, nodal analysis had to do with the node voltages, so the mesh analysis is going to deal with the branch currents. So I'll draw the same basic example as last time. Looks something like this. Just a simple network. So V1, R1, R2, R3, and I1. So remember, with nodal analysis, you would pick you would find the unknown node voltages, and then write the KCL. Well, with mesh analysis, remember a mesh is simply a closed path where you can draw a loop. So this is a mesh right here, and say you have 2 meshes like this. So this would be 2 meshes, but if you drew a loop like this, well, that's not a mesh current. A mesh current has to be within one singular branch like this. So this is 2 meshes. Although you can draw one whole loop for this one, that's not how you do the mesh analysis. So with mesh analysis, you only draw branch currents over one mesh. So notice in this circuit, in the example, we have 2 meshes. We have this one, I'll call it I1, and this one, I'll call it I2. So with mesh analysis, the M number of meshes equals M number equations. So that being said, compared to nodal analysis, how you solve these problems, one technique might be easier over the other. Like for example, in this example circuit, you would want to use nodal analysis because you only have one unknown node. But if you use mesh analysis, you have 2 unknown meshes. That would lead you to have 2 equations. So then you'll have a system of equations rather than one equation to deal with. But for the sake of understanding mesh analysis, we'll go ahead and mesh this up. So remember, the mesh analysis, the basis is now the KVL, the Kirchhoff's voltage law, which states the voltage drops across every component in a closed loop has to equal 0. So given my arrow, you want to follow the arrow just like nodal analysis. So I'll start from here and then follow the arrow, which is going that way. and I'll add the voltages up. So for sources like this voltage source, you start with a minus, because it's going up into the minus, so minus V1, plus, and then by convention, for mesh currents, you'd always say the current going from one terminal to the other, it always enters the positive and then out the negative. So this would go, by convention, the arrow would go into the positive and out the negative. So it'd be plus I times R1, because remember, that's Ohm's law, because Ohm's law is V equals IR, or V equals R times I, which is how you do the KVL. You use V equals IR. So that's the voltage across this resistor, plus, well, I'm still following, I have this resistor here, following the arrow, this R2. So for this one, it's going to be I in this case. Well, notice I have two meshes. So I'll draw a bigger picture. So let's say this is R2. I have, this mesh, I called I1, and then the other mesh, I had I2, which is going like this. So you actually have to take I1, the one you want, and subtract the mesh current that you don't want from this mesh. So it's I1 minus I2 times R2. And that completes, equals 0, and that completes the Kirchhoff's voltage law for this mesh. KVL at I1. So now we still have to write the KVL at I2. So following the arrow, I'll just start from here. So remember, it goes into the plus and out the minus. So it's going to be, a positive number. It's going to be I2 minus I1, because remember, this resistor is in between the two meshes. You have to subtract the one you don't want. I2 minus I1 times R1, and then plus I times R3, and then this current source would actually be the current flowing in this branch. So this I2 is actually equal to the I1 itself. So this I2 is I1, and this would just be I1 equals 0. So that's how you do the mesh analysis. So let's go ahead and do some examples. Let's find one. Mesh analysis examples. See if we can find a basic one first. So let's see what we got. Basic one. This one's pretty simple. Start with this one for now and then do a harder one after. So let's write the mesh equations for this circuit here. So we have two meshes. This is I1 and this is I2. So the KVL at I1, well, that's going to be, let's say I just start here and follow the arrow. Well, negative 20 plus 5 I1 plus 10. Well, that's a resistor between two meshes, so it's going to be 10 times the current you want, which is I1, minus the current you don't want, which is I2. That's equation 1. Then we have to write the KVL at I2, which I'll start from here. So it's going to be R, which is 10, times I2 minus I1 plus 30 I2 minus 80 equals 0. Oh, sorry, this equation equals 0. Always forget that. And that's equation 2. So then to solve for I1 and I2, notice you have two equations and two unknowns. So now it's just a math problem. So let's look at a harder example. Let's see if we can find a harder one. Any hard ones? Let's see. Maybe sums with like current sources. Those tend to be a little more confusing. Let's see. Not really seeing too many complicated. Let me see this. Usually these get some good ones. Alright, let's see. No. Actually, yeah, let's do this one. Let's just do this one to get some dependent source action. So using nodal analysis, we have to find V0 in the circuit. Okay, so we first write the mesh currents. Call this one I1, and this one I2. So KVL at I1 is going to be, start from here, well, it's 4I1 plus 6I1 plus, that says nodal analysis. You know what, that's fine. You can solve it either way. We'll use mesh. I'll say mesh analysis. Okay, 4I1 plus 6I1, and then we're going down here, plus 60 plus, now this resistor is in between the two meshes, so we have to do 20 times I1, the current you want, minus I2, and this is going to be equal to 0. That's equation 1. Now we have to do the KVL at I2. So starting from this point, we get 20 times I2 minus I1 minus 60, minus because I'm going into the minus of the voltage source following my convention, minus 60 plus 20 I2, then into the plus of this dependent source plus 5 V0, all equal to 0. That's equation 2. So notice this circuit has a dependent source. So in this algebra problem, well, V0 is this voltage here, which depends on this voltage source. So the first thing you have to do is find V0, which is actually the point of the problem. But you have to use this dependent source because it's 5 times V0 to solve the problem. So 2 equations, 2 unknowns, and that's how you would do it. So that's it for mesh analysis. Now the next one, which are operational amplifiers. So that basically sums up resistor networks. Operational amplifiers are a little different. They're kind of like resistor networks, but not really. They're kind of different. You can't just use Ohm's law for them. So I'll go ahead and explain those. So just to recap, resistor networks are basically just voltage sources, current sources, dependent or independent, a mixture of all of them, and only resistors. So remember, the 2 techniques to solve them are mesh analysis and nodal analysis. Those 2, pointing to resistor circuits. So those are 2 techniques you would use to solve resistor networks. So next are operational amplifiers, or op amps for short. So what are those? Well, this might be a review, but if it's not, here we go. So an op amp is simply just a device that has 3 terminals, unlike a resistor, which has 2 terminals. So remember, a resistor has 2 terminals, which we have terminal 1 and terminal 2. But the op amp has 3. You have 1, 2, and 3. So how does this thing work? Well, the op amp has these signs here, this plus and the minus. What does that mean? Well, that means the voltage, or basically what the op amp does is it takes the voltage across these 2 terminals, V plus minus V minus, and what it does, the op amp, it subtracts, or it multiplies it by a very large number, A. And that is equal to the ground voltage, which is some voltage between here and ground. And that's how an op amp works. So there's 2 golden rules. The golden rule, or the first one, is V plus minus V minus has to equal 0. So what that means is any change in this terminal of either of the terminals, it'll push the other terminal to the same voltage, if that makes sense. So say you change V0, or let's say V plus equals, let's say 10 volts. Then that means V minus would also be pushed to 10 volts. So that's the first golden rule. Any change of voltage in these terminals will push the other terminal to the same voltage. And then the second golden rule, are the currents going in and out. So let's say this one is V1 or I1, this is I2, and say this one's I0. So current, the second golden rule is current cannot flow in or out of the input terminals. So the input terminals are V plus and V minus. So that means I1 equals I2, which equals 0 amps. However, current can flow in and out of the output terminal, which is usually what it physically happens is there's power rails that power the op amps. I don't know if you know from 1202. So current can flow this way, like this, but it cannot flow that way. So that's the second golden rule, and those are really important for the op amp. So let's show an example that has these golden rules in action. So the most basic example would be called, well, I'll just draw a circuit before I name it, is something that looks like this. So this is probably the most basic op amp circuit there is. Let's call this Vn. Sorry, that's bad. Vn over here, and over here would be Vout. Actually, make it easier to read. This terminal will be also connected directly to ground, even though it's the same node. Excuse me. So that's Vn between these two terminals. Vn. So say you wanted to find what Vout is. You want to know what that is. Well, how would you do that? Well, what you would do is, well, remember, current cannot flow in or out of the op amp. So you would basically take this node right here, and it'd be a dummy node. I'll call it Vx, and I'll call this current Ix, flowing into the op amp. And then I'll have to draw one more current. Let's call it I2, and this one is I1, the current flowing through R1. So the KCL, it's going to be current flowing into this node equals current flowing out. Well, it's going to be I1 plus I2 equals Ix. But remember, Ix, this has to be 0, because remember, current cannot flow into the op amp. So Ix is going to be 0. Then we just have I1 plus I2 equals 0. Well, now you can write just the nodal analysis equations. So I1, well, it's going to be Vn minus Vx over R1 plus, well, I2, that's going to be, well, this node, because the arrow is going this way at the start from this node, which is going to be the voltage Vout. Sorry. Vout minus, going this way, minus Vx over, sorry, that's R2, over R2. And this is equal Ix, well, remember, that's 0. So from these equations, remember, we have to look at the first golden rule. Well, Vx is a dummy node. There's no voltage source on this branch. Therefore, there's no voltage on this node. That means Vx is also equal to 0. So Vx is 0 volts. Like, for example, why that is because this plus terminal is connected to ground, which is 0 volts. But let's say hypothetically, because this might be confusing for people, so I'll show you how it works. Let's say there's a voltage source here, Vs. Now, if there's a voltage source here, then what that means is, using golden rule number 1, well, Vx would be pushed to the voltage Vs. So this Vs here magically makes this node Vs. That's just how op amps work, the golden rules. So that's why if it's shorted to ground from that plus terminal, then it's going to be 0 volts. Vx is going to be 0. Let's clean this up. So this is connected to ground like that. So that's why Vx is equal to 0. Now the equation becomes Vn over R1 plus Vout over R2 equals 0. So using some simple algebra, we see that Vout equals negative R2 over R1 times Vn. And notice that this equation matches the form of the equation for the op amp. It takes the input voltage, which essentially the voltage here is Vn, that's essentially the input voltage, and multiplies it by a large number, A, which in this case is negative R2 over R1. So what you can do is basically choose R2 to be much larger than R1, and you'll boost, or it's called gain or amplify, you'll amplify Vn to be a number, or Vout would be a number larger than Vn. That's why it's an amplifier, the operational amplifier. So that's how op amps work. You want to follow the golden rules and then use nodal analysis to derive the equation. And one thing to note later in the course, this equation here, Vout divided by Vn, well in this case it's negative R2 over R1. Well, that's called the transfer function, which is basically an equation, the transfer function. It's just an equation that models every output for every input, which is Vout divided by Vn. It's every output per every input is equal to this number. So that's called the transfer function, which will be useful later in the course, as we'll see. So I think that's good for operational amplifiers. Remember, just follow the golden rules and then write the node equations, and they should be good. So next are energy storage elements. So energy storage elements, what are those? Energy storage elements. Well, if you think about it, energy storage elements would be just capacitors and inductors. So the first one, usually go over the capacitor first. The capacitor. So the capacitor is also a two-terminal element, just like a resistor, with this constant C, a voltage across it, Vc, and the current. Current in DC doesn't flow through the capacitor, so I say the current that it's charge really that flows to the capacitor and charges the plate, IC. So the equation that represents this two-terminal component, remember, for a resistor is V equals IR. Remember that. For a resistor, the voltage current relationship, so this is voltage across the resistor, R is a constant, IR. Remember, the equation that represents this component is V equals IR, which is Ohm's law. But for capacitor, it's a little different. It's going to be the current to the capacitor is equal to C times derivative of the voltage across it. So what this equation is telling you is that any change in the voltage across it allows a current flowing, usually people say through the capacitor, I guess that's what I'll go with. Any change in voltage across this capacitor makes a current flow through it times the capacitance C. So C dV over dt equals I. And another thing is to note, they're energy storage elements. So the energy stored in it, it's a function of time, equals 1/2 CV of t squared. So it's proportional to the voltage squared. So if you think about it, what that basically means is, if you look at it on a graph, the potential, so it's a quadratic. So the potential, it's going to be E of t versus time. So it has these 2 points it usually bounces between. It goes this way, then this way. That's why the capacitor, you know, like it charges and discharges. Let's say this is negative x naught and positive x naught. So if you think about it, the capacitor charges and discharges like voltage basically. So it's basically equivalent to like a spring. So, you know, a spring compresses and decompresses. That's the analogy of the capacitor charging and discharging. It stores a voltage and then can release it, which makes the energy go back and forth like this on a quadratic. So that's the energy stored in the capacitor. And so next would be the inductor. And so remember earlier how I mentioned dual concepts. So that's going to be the capacitor, which is C dVc over dt equals I. Well, for an inductor, let's see what the equation looks like. For an inductor, also a two-terminal component, let's see, this would be VL, the constant inductance is L, and the current through it is IL. The inductor through the current through the inductor. So the equation to represent this two-terminal component is VL. Remember, these are functions of time. I'll mention that here. VC of t. These are all functions of time. VL of t equals L times the derivative of the current over dt. So notice there's a dual concept. The C dV over dt for the capacitor, this is for a cap, and then it's L dIL over dt for an inductor. So they're dual concepts. This equals IC, but this equals V. And this is for a inductor. So they're just like reversed, you know what I mean? They're almost like they're almost like brothers, you know what I mean? They're just like related to each other. It has the same structure of equations. So for the capacitor, it's the change in voltage allows a current to flow, but for the inductor, the change in current induces a voltage across the inductor, which is, remember, that's Faraday's law. So this component also stores energy, and the equation you can imagine has the same structure. It's 1/2 Li squared. So an inductor, what the analogy would be, it'd be like a mass. You know what I mean? It's like the current, or like a water wheel. That's probably an easier analogy to understand. So a water wheel has to have, how would you draw that? I don't know, I guess like this. So you have, say, like water like this, and then it's gonna push it this way. So the water, sorry, that looks bad. You'll say you have like a water pump, and then it's pushing it this way. So if you could think about it, a water pump would take, the water wheel would take a while to get rolling, but once it does, that thing will stay rolling for a while. And then say you just stop the water from pumping water. Well, logically, if you think about it, this water wheel will keep spinning until the energy has been dissipated. So that's basically what an inductor does. You have to put a voltage across initially, and then current will flow through it, but it slows the change in current, just like how the capacitor slows the change in voltage. So the capacitor smooths, that's usually what they say, it smooths the voltage, and the inductor smoothens the current. So those are the basic concepts of the energy storage elements and the basic equations. So we'll get more into those circuits, or we'll get into circuits including those for exam 2, but this is for exam 1. So I'm not going to get into circuits that include energy storage elements. So it looks like the last section is the Thevenin and Norton equivalent circuits. So these are two network theorems that are really important, also really powerful. So Thevenin, and they're also basically the same thing. Thevenin is Thevenin's theorem states that any resistor network, so let's just draw a random one, any resistor network containing only, in this case, independent sources, so it has to be either independent voltage or current sources, and resistors. I'm just going to draw some random looking circuit like this. Any circuit like this containing only independent sources and resistors can be reduced to this very simple circuit, which is a voltage source with a value of V Thevenin, usually it's V sub TH, that's what we call the V Thevenin, in series with the resistor, and it's two terminals poking out of a black box. So let's say this circuit has these two output terminals and the rest of the circuit is inside of a black box. Well, inside the black box, you can reduce it to this very simple circuit. A voltage source in series with the resistor, which usually they call it the Thevenin resistance, or generally it's the R equivalent, the equivalent resistance. And that's the Thevenin's equivalent, or Thevenin's theorem. Likewise, for Norton's theorem, would be basically the same thing, but for a current source. So how does that look? Actually, I'll keep this. So for Norton's theorem, sorry, hold on, let's write it down. Get rid of this, this. So for Norton's theorem, number 2, Norton's theorem, Norton's, looks so bad. ER theorem, whatever, sorry. Norton's theorem states any resistor network, and this is inside of a black box. So that is Norton's theorem. And so there's another concept called source transformation, which is how you go from the Norton and the Thevenin, how you go in between them. So let's say I have the I Norton right here. And this resistor has a value of RTH. And say I want to go in between the two, like this. V Thevenin and RTH. Oh, sorry. Then this is inside of a black box. Oops. Here, let's draw that arrow better. So what do you think you would do if you had to go in between them? Well, the way to do it is actually using Ohm's law. So from Ohm's law, V Thevenin equals V equals I times R. Well, it's just going to be I Norton times R. And likewise, I Norton equals V Thevenin over R. So that's how you switch in between. Sorry, R equivalent. So R equivalent always stays the same, this R EQ. However, these sources, you can go between them by using these two equations, which is basically just Ohm's law. And that's called source transformation. So you can use source transformation and Thevenin and Norton's theorem to simplify your circuits to make them much easier to solve. And it looks like those are all the topics for exam 1. So I'm gonna go ahead and stop here, and thank you guys very much. And good luck on the exam. Also a reminder, I'm gonna have a live session on Monday doing the exam from last year. So stay tuned.